What's up, calculus students? Lesson 2 homework. It's a new homework. New homework I created, focusing on displacement. Okay, displacement, change in position. What we learned is that there's two ways to calculate this displacement, this change in position. The obvious way is to just find your position kind of in the future and subtract your position in the past. But what we also discussed and discovered is that if you have a velocity graph, that whatever your velocity looks like, that the accumulation of this velocity or the area under the velocity, that's also going to be the same as displacement. Why is that? It's like distance equals velocity times time. That's a formula you might be used to from physics. Cursor comes back. Distance equals velocity times time, and it's really displacement equals velocity times time. So like take all these velocities times these split seconds at they're at. So like all of these velocities at the moment in which we're taking that velocity, add them up, accumulate them all, boom, you'll get displacement. So now we have this new thing where we're going to kind of combine these two ideas, where we'll say, okay, take your velocity curve and accumulate it, find the area under it. Okay, we're going to understand that since to calculate a displacement, you could accumulate velocity. It's the same as finding the change in position. What we're going to do is use this integral, which we know as take the antiderivative, to say, oh, okay, this integral now means accumulate velocity. And the way we can accumulate velocity is by taking the antiderivative and doing this alternate approach by finding the change in position. Take the antiderivative of velocity, get position, and find the change in position. This little line just means like I'm going to plug in 3, and then I'm going to subtract 1. Now, if we had a calculator, which we will, our calculator actually can accumulate very quickly. It can do a bunch of quick velocity times over an interval, something that we can't do as humans very quickly. We can't do all the arithmetic quickly, but the calculator has the capabilities of doing it quickly. So the calculator can find this accumulation without taking an antiderivative. What we're going to have to do is take the antiderivative to get this alternate approach. Okay, so two ways to do it. This is how we're going to do things by hand. To find like an area, to find the accumulation, we can use the calculator, and we'll be ready to do both after the end of this lesson. So I'm starting with questions that are no calculator. I'm giving you a velocity over an interval. And I'm saying, what's the displacement? What's the change in position? Well, we'll start out and saying I need to accumulate velocity. Instead of writing v of t, I'll write 2t plus 1. And I'm going to accumulate it from 1 to 3. But that's the same as taking the change in position. I'll take the antiderivative, and I'm including a plus c, and I'm going to find my position at time 3 and subtract my position at time 1. So my position at time 3 is going to be 9 plus 3 plus c. I don't know what c is because I'm not given an initial position. And then my position at time 1 will be 1 plus 1 plus c. Now, because this is the same c being used, this is not like c1 and c2. This is like one number, and that's the same number. When I subtract those two things, the c's will cancel. So what I'll tell you is that you can essentially ignore the c when you take the antiderivative when we're subtracting the antiderivative at two different points. So you'll just get 12 minus 2, or 12 plus c minus 2 minus c, and that gives you 10. So my displacement is 10, or you could say from 1 to 3, I've displaced 10 units to the right. So my dude has moved And remember, like all we have is, I'll use this as the number line, a dude on a number line over the course of 2 seconds. You don't say that he's only moved to the right 10. You got to be careful with that. You're just saying, like, at time one, he's at a location. Where it is, I don't know. But then when I stop the stopwatch at time three, he's displaced 10 units and ends up over here. Okay. And we're just going to continue to do that. We'll accumulate velocity, which will be the same as finding the change in position. Take the antiderivative, include the plus c, but the c won't matter because the c's will cancel. This is -6 plus 1. The c's will go away. The c doesn't matter. And here we have a displacement of -5. So overall, over these 2 seconds, I've moved to the left 5. Maybe I moved back and forth a little bit. Maybe my distance is different. But between those two times, that's my displacement. Okay. From 0 to 2, if my velocity is t squared, this is a common one I will talk about in future classes. Take the antiderivative. We don't care about the c because they'll just go away. Eight-thirds, my displacement is 8/3 units to the right. Okay. Let's accumulate our velocity from 0 to 3. That is the same as finding my change in my position over that time interval. Take the antiderivative to get my position function. This will work out nicely. Here we'll get 27 minus 27 plus c minus 0 minus 0 plus c. The c's will cancel. You end up with 0. Now it's like, oh, my guy didn't move on my number line. In reality, what happened in this situation, I don't know where my dude is starting, but my dude is probably going to be moving for like half the interval or for part of the interval in one direction, and then he'll move back in the other direction, getting back to where he started, giving me a displacement of 0. So he ends up back at where he started at 3 seconds. Okay, it's not a distance; it's just like an overall change in position. That's not the right stuff.
Are you recording again?
Okay, my velocity is 6 sine t. Obviously, my velocity is positive and negative, so like my displacement might be 0, it might be negative, it might be positive. It all depends on my interval. I'm going from 0 to pi. To accumulate our velocity to get our displacement, our velocity times time. The alternate way to calculate that using your calculator is to take the antiderivative to find the position function and to find the change in position. Antiderivative of sine is negative cosine. We just have to remember the derivative of cosine is negative sine, so I need a negative cosine to get a positive sine. C won't matter. I'll keep putting it in here. Cosine of pi is -1 times -6 is +6. Cosine of 0 is 1 times negative 6 is negative 6, but I'm going to be subtracting it. So subtracting negative 6, adding a positive 6. And if you distributed this negative, and this is what I would recommend you do, you realize you're still subtracting c's and you get a displacement of 12. So overall, I've displaced the right 12 units. So I don't know where exactly the guy started, but wherever he started, over the course of pi seconds, he's going to the right 12. Now, if we look at the velocity 6 sine t, it looks like that, and that's pi because that's when I get a 0. So it looks like I am going to be moving to the right constantly. And at pi, I'll change directions. So this is like the total amount that I've gone right. I didn't go right or left at all. If it's 6 sine pi t, just be careful when you take the antiderivative to get your position function. You got to remember lesson 2 from last unit. We got the negative 6 cosine. That's the antiderivative of the outside, but we need to undo the derivative of the inside. I need like a 1 over pi. And that's the position function. Find the change of it between 1 and 0. So x of 1 would be negative 6 over pi cosine pi plus c. Then x of 0, negative 6 over pi cosine 0 plus c. Distribute the negative. This will be positive 6 over pi plus c. And this will be positive 6 over pi minus c. The c's go away. I didn't need the c to begin with. Don't need the c to begin with, but I'm just going to keep putting it in so we don't forget about it. And I have 2 6 over pi's, or I have 12 over pi's. I have like 6 1 over pi's and 6 1 over pi's. 2 6 over pi's, which is 12 over pi. Okay, and that's our displacement. That's our change in position. That's how much my guys moved. Okay. Now, there are going to be situations where you're going to be given a velocity, example, this guy, and you're going to try to find the displacement. And if you keep the one method in your brain of, oh, I have to take the antiderivative to get the position, we'll run into a problem. You can't take the antiderivative of t to the 2/3 cos t plus 2. You might think antiderivative of this, antiderivative of this, but you can't because it'd be a product. So it's like my position function here, I have no idea what it is. So what are we going to do? This is when we're going to just use our calculator and our calculator's abilities to find the accumulation, to find the area under this function. So let's get our calculators out. And I'll show you the two ways to find this accumulation, this area. If you see on your calculator in math, underneath n derive is fn int. This is like take the integral, find the accumulation, find the area, and you can type in exactly what you see. Now, what your calculator does is they don't, and I don't care if it's x's or t's, just use x's, make them represent t's. It's not going to take the antiderivative here, but what it's going to do is, and you'll see your calculator will work hard. It'll take a while to get the answer. It'll do a bunch of arithmetic really, really quickly, and it'll provide a good approximation for this area, this accumulation. And it immediately gets you the answer. It did take a little bit of time, negative 0.885. Now, what's going to be really helpful for us is to graph this and see exactly what's going on and see, like, why did I get this area, this displacement of negative 0.885, which means I'm moving left overall from the second to the 8th second. So frequently in the class, best thing to do is to graph. Make sure your calculator's in radian mode. Make sure your window is set for what you're looking for. I'm looking from 2 to 8. And it's important to understand what we see here. Okay. So what I have here is the graph of velocity. Now, if you remember, like when velocity is negative, position's decreasing, velocity is the same as x prime. So I'm going to the left, then going to the right, then going to the left. But what I'm saying is that this area under the velocity will tell me how far I've gone left, how far I've gone right, how far I've gone left. And your calculator can accumulate these velocities, find this area using the home screen, or go to number 7, the integral, and then it says lower limit. And it's like, well, I'm going from 2 to 8. You press 2, press enter, and it sets the lower limit. Upper limit, we're going to 8. So when t is 8, now it says x, but it's t. And look, what it's doing right now is accumulating. It's doing a bunch of arithmetic and calculating this negative 0.885. Okay, so I'm going left. We could calculate how far we've gone left. I'm going right. We can calculate how far I've gone right. Then I'm going left. Put them all together. I've will end up just to the left of where I started because I went to the left a little bit. I went to the right some more, but then I went to the left even more than that. So I'm back close to where I started, probably close to where I am at this time. I hope this makes sense to you. This is important stuff. This next one, it's the same deal. You think, oh, let's take the antiderivative. You can't. You don't know what the antiderivative of t times sine t, this product, makes things difficult. Compositions will make things difficult. So instead, we'll just let our calculator do the work for us. And our calculator will do a bunch of arithmetic to approximate this accumulation of my velocity, these velocity times times, which is displacement. Okay, and I see that overall, over this interval, I'm going to be displaced to the left. I'll end up negative 6.478 units to the left of where I started, wherever I start. I don't know where I've started. They're not giving me any positions, but at least I know the displacement between the two intervals. So there's one way, the other way, t, sine t, and we'll be using these again. I probably should just keep them in here. So yeah, I'm going to keep them in here. And I'll just hide them when I don't want them. Okay, so that was the first one, which we will be using again. Here's the second one, t sine t, which I do want to see. Change my window from 4 to 7. I'm moving to the left, and then I'm moving to the right. Now, the accumulation would be how much I've moved left. My change in my position. The accumulation is when my velocity is positive, how much I've moved to the right. Put them together, it's the overall displacement. Moving to the left a bunch, moving to the right a little less than that. Overall, I'll displace negative 6.478 units. So second calc, 7 from 4 to 7. And it's nice that it shows you like that. And there's that answer. Okay. So left, I don't know, like 10, right, 4. And we'll find this in the future, like what's this spot when my velocity is 0, when my position hits a minimum? How far have I gone left? How far will I go right? We'll find this spot later in the homework. Same deal, this third one, hide this guy, 40 e to the negative t, use x, sine x, minus 5. Okay, and I'm just going to do this method. Change your interval. Pause is on. On is a quick little pause. Don't go from 4 to 7, go from 0 to 3. Okay, so I'm going to the left a little bit. My velocity is negative. I'm going to the right a lot. All this area is definitely more than this area, this accumulation. And then I'm going to the left. I think I'm probably going to end up going to the right a little bit overall over this interval. Second calc, integral, the lower limit is 0. The upper limit is 3. Going to the left a little bit, going to the right a lot, going to the left some. I overall displaced 5. I'll end up 5.84 units to the right of where I started at time 0 when I get to time 3. I end 5.845 units to the right of where I started. Where did I start? I don't know. I don't know where I started. But that's it. And then this fourth one. And we will like find out like where did I start? Where did I end up? Later in the homework. Okay, we'll incorporate an initial position to see what we can do, and that starts with the next one. Okay, so I can see my velocity is positive. I'm moving to the right. The accumulation of velocity will be how far I've moved right, and then I move to the left. I don't know. I might end up like back where I started. It looks like maybe this accumulation, this area is the same as this negative area when my velocity is negative. So let's find out. My window's from 0 to 3. Good. Second, calculate from 0 to 3. All right, I ended up just a little bit to the right of where I started. Now remember, like I go to the right and then I go left and I end up, here's my dude. Where he starts, I don't know, but I go to the right a bunch. I go to the left some and I end up here after 3 seconds, 1.047 units to the right of where I started. I like how I can say that. I ended up. Okay. I could have said that for all. Okay. Now, where did I exactly end up? Where is my position that I ended based on a position that I know that I started in? We've been able to do this. We did this last class, but now we'll find that there's another approach to find an unknown position, a missing position. Okay. So we already know how to take an antiderivative of v. We know v is the same as the derivative of position, x prime. And I want to find x of 3, but I'm given an initial condition, x of 0 is 4. We know we could take the antiderivative. Now notice I'm not putting any numbers here because I'm just going to take the antiderivative. I'm just going to have a position function, which is negative t squared plus 3t plus c. And this is my position function. But I know I have a position, x of 0 is 4. And I can find c. All of a sudden, we can find any position we wanted to. Okay? And if I want to find x of 3, plug in 3, I get negative 9 plus 4, which is 4. Okay, so this is where I ended. But now we have an alternate approach. Okay, using the fundamental theorem of calculus, the equation, the equivalency of accumulation of velocity here over the interval from 0 to 3. That's the time that I started, that I know the position at, and the time that I ended, that I'm trying to find. The accumulation of this velocity will be my displacement. And we know that's going to be equal to the displacement, the accumulation of velocity. The displacement can be calculated by finding x of 3 and subtracting x of 0. Well, if I want to find x of 3, watch what I can do. I can add x of 0 to both sides and get this equation. My initial position, or the position that I know, plus my displacement between the two positions will give me my unknown position. Now, the displacement between the time 0, which I know, and the time that I don't know, that I'm trying to find. And this is an equation that we can use. It ends up being like very similar calculations to what we just did, because we'll be taking the antiderivative. We have the capabilities of doing this without a calculator, but we'll see it'll just be a little bit different. Now we like to kind of write this so that like my unknown position equals my known position plus my displacement. This is kind of what we get to this formula, and we'll use this formula. Okay. All right. Well, I have my unknown position, or I have my known position, x of 0 is 4. So I'm going to say x of 0 is 4. Now to calculate my displacement, I'll take the antiderivative and plug in 3 and plug in 0 and cancel the c's. Don't worry about finding c. I'm not going to worry about it at all. I'm going to take the antiderivative, find the change between 0 and 3. The c will go away when I subtract. Negative 9 plus 9 is 0 plus c, and then 0 plus c. The c's will go away. The c doesn't matter. And we get just this 4. Same answer, just we got it a different way. Now, if you don't have a calculator, probably the method that I would recommend you use is this method, because it's familiar to us. It just makes sense. It's like we can find this plus c. You'll see with our free response questions, I'll have something like that, and you'll have two different ways, but this way is easiest. It's familiar to us. But when we have situations like this guy, where we have a calculator and we're given a calculator because we can't take the antiderivative, this alternate approach, this fundamental theorem of calculus, this area, this accumulation method, this is going to be the way to find this. You want to find x of 8? Well, I know that at x of 2, I'm at 3. If I know my displacement, my change in my position between the two, I'll know where I end up at 8. I believe I already found this, 2 to 8. Yeah, so like, boom, those numbers are available to us. I actually wish I did them on the home screen. So, and then I can visualize this on my number line. I started at a position of 3. I then displaced. I moved like right and left a bunch, but in the end, I've displaced. My overall change in position is negative 0.885. Now I know where I ended up. Now let's look at that. Back to the first one. 2 to 8. Okay, so I moved to the left from the second second to this second. I then moved to the right till this second. And then I ended up moving to the left. So I move a lot, and I'll show you that on the number line. I started at a position of 3. So here's my position of 3. Here's my dude at a position of 3. And this is at t equals 2 seconds. Okay? Between 2 and 8, I'll move left an amount. I'll move right an amount. I'll move left an amount. So I move left a little bit. We can calculate that if we wanted to. I move right a bunch, but then I end up moving back left, maybe a little bit less, maybe a little bit more. I'm not exactly sure. And where do I end up? In this position to the left 0.885 units at t equals 2.114. I just added those two numbers together. So here is me ending up at 2.114 after a total at the 8th second, not after 8 seconds. It's like from 2 to 8 seconds. I started at a position of 3 at time 2. I moved left a little bit, right a little bit, left some more. I ended up a little bit to the left of where I started. That's motion. That's what's going on. Position increasing, decreasing, right, left. It's like what we've done before, but now this whole area thing is new to us. And what we'll eventually do is go back to f primes and f's and understand that the area under f prime, the accumulation of f prime, gives us the change in f, which tells us how much my function is going up and down. All right, so here I want to find my position at time 7. I know my position at time 4. Let's find my displacement, which I found earlier. My accumulation of velocity. I can't take the antiderivative. I use my calculator. I started at a position of 2 at the 4th second. -2 at the 4th second. I then add my displacement from 4 to 7, which was -6. I'll end up a position at -8.478. This is -6.478. Let's see what the graph of my velocity looks like, and let's kind of understand the movement of my dude from the 4th to the 7th second. All right, so my dude's moving left a bunch, and then he moves to the right a little bit. So here's my dude. He starts at a position of -2. He's here at the 4th second. My velocity is negative, so I move to the left a whole bunch. And then I end up with a positive velocity. X prime is positive, X is increasing. I'm moving to the right. How much? A little bit less, definitely less than how much I move to the left. So I move to the right a little bit. Where do I end up? My overall displacement was -6.478 meters. I end up at a position of -8.478 meters. And here I am at this position after 3 seconds from the 4th second to the 7th second. Okay? And it's important to keep this kind of idea in our brains for the next lesson when we're talking about where we have max and min positions. All right, what's x of 3? I have x of 0. I have the displacement, which my calculator will use to find. I already calculated it, but I'll do it again It's easier to do this calculation. It's 5.845, but I'll do it exactly. So I started position of 3. I've displaced 5.845. I'll end up with 8.845. This is from 0 to 3. Again, I move to the left a very little because my velocity is negative. I move to the right a bunch. I move to the left a little bit less. My overall displacement is to the right. I started at a position of 3. This is my initial position. When t is 0, I move to the left a little bit until this moment in time. We can calculate that. I move to the right a bunch, and then I end up moving to the left some. Where do I end up? 5.845 units away from where I started. That's my displacement. I ended up at 8.845 at the third second. And let's just calculate that. 3 plus, or probably good to separate them out just so we can see. Here's my accumulation of my velocities times my times for all of my split seconds. There's that 5.845. Add that to 3. There's my position at this third second. Same deal. What's my position at my third second? But I know my position at the 0th, the 0th second, and this will calculate my change in my position. So I started at a position of -4. My displacement was 1.047. I'll end up at like the -2.9 something, 9/6 position. Let's just do it quickly. From 0 to time 3. My displacement between those two times, a lot of people mess up and they'll put -4 here. But it's like from this time to this time, how much did my position change? And this is what that's calculating. There's that. Add that to -4. And that's my position. But let's look at what that looks like on my number line with my dude. Here's a position of 0. Here's my position at -4. Here's my dude. Starts here. T equals 0. We'll look at this. We're going from 0 to 3 as well. I go to the right, and then I go to a left. I go to the left less than I go to the right because my displacement is +1. So I end up going to the right a bunch. I go to the left almost as much as I went to the right, but not as much because I end up just to the right 1.047 units away. So I end up at -2.952 here after 3 seconds. Okay. But that's my motion. You can think of this as my position graph. My position's increasing, then decreasing. Where do I end up? Now, what if I ask you for a missing position from the past? What if I say, hey, I know my position at time 6. What was my initial position at time 0? Well, this is where And I do this a little bit differently depending on the situation. We have options. If we use the formula we've been using, this is how it would look. My position in the future equals my position in the past. It used to be my known equals my unknown, but let's just go with this. Position in the future equals my position in the past plus the displacement between the two. And now all this is just an equation that we have to solve. This is 3. I don't know what this is. I can calculate this using my calculator. This is where if you have it in the home screen, it's actually beneficial because we can go back to the t to the 2/3. Instead of going from 2 to 8, I'll see what my displacement was from 0 to 6. So overall from 0 to 6, see how your calculator is working to figure this out. My displacement was 3. So like I started somewhere, I moved to the right and to the left a bunch. I end up 3.147 units to the right of where I started. So how can I figure out where I started? Well, we'll just subtract. It's like, well, this plus this has to equal 3. So like take your known position, subtract your displacement if you're going back in the past rather than adding. Subtracting displacements from the past rather than adding should make sense to you. It's like starting plus my displacement will get where I end. Starting will equal ending minus displacement. Okay, so here, my dude started just to the left of the origin at t equals 0. Then he displaced a bunch. We could look at the graph moving right to the left. And where did I end up? At the 6 second, I ended up at position of 3. Okay, same deal. Now, if you wanted to, you can immediately just have it solved for. It's like my unknown position from the past equals my known position in the future. And then instead of adding my displacement between the two from 1 to 4, I'll subtract my displacement. I don't think that's necessary to do. I think it's probably better to say future equals starting plus my displacement to the 2, solve the equation. I think it's just easier to keep in your brains. -2 is where I ended. Let's see how I traveled from where I started to get to where I end. And then I'll subtract to be able to see where I started. It should make sense to us. I think I have t sine t somewhere. Right there. Now I'm going from 1 to 4. 1.556. Subtract the 2. Since I moved to the right between this position at time 1 and this position at time 4, I must have started to the left of where I ended, so that I ended up displacing to the right to get to this negative position. Or I just solve the equation by subtracting. Okay, so dude, -3.556 is where he started at t equals 1. He ended up at a position of -2 at t equals 4. How he got there, we can look at the graph to see if he like went right and then back left or something like that, or left and back right, something like that. Look at the velocities, see when it's positive, negative to see things. All right, let's just do the last 3 kind of quickly so we can move on. I don't know my initial position, but I will be able to find my displacement between the two, my change in my position. Are we staying from 0 to 3? Yeah, we're staying from 0 to 3. That's nice. 0 to 3, 0 to 3 seconds. What's my displacement? So I will have to move 5.845 units to get to a position of 5. Where did I start? 5.84 units to the left of 5. Subtract. Solve. That's a position. And here I have x of 4. I don't know x of 2. I'll be able to find the displacement, the accumulation of my velocity times times. This is negative 4. I don't know this. Let's find this. It's t squared cos t plus 2. We're going from 2 to 4. It's all about seconds. What my accumulation of my velocity is over this time frame. Wow. So I have to go to the left 11.978 meters to end up at a position of negative 4. So I needed to start 11.978 meters to the right of this position so that I can end up there. So we add that number to negative 4. We subtract that number, but we add the positive number, if you want to think about it like that. Okay. All right. Now we start getting into some extra stuff that we have to do. We need to figure out when my particle changes directions and what my positions are at those times. Okay. Now, when is the particle changing directions? The particle is changing directions when the velocity changes sign. Typically, it's going to occur at a 0. Right? Because we remember if velocity, which is x prime, goes from positive to negative or negative to positive, x will go from increasing to decreasing, or what we like to call it now, from right to left if we're talking about on a straight line. So it's this 0 where we're going to change directions. So we're going to find the zeros. So what we're going to do is go into my y equals, and we're going to look at the graph of my velocity equation over my time interval, but I'm also going to include my friend y equals 0. I'm going to have that always graphed. You'll be able to see it in bold. Okay? Make sure your window's adjusted, or else you'd have to pause and then change it and then go back. We're going from 0 to 8. Okay, so there's one location where my velocity is 0. There's a second location. I'm hoping it's just 2 and not 3. Good. Okay, now I know we start at 0 because if I plugged in 0, I'd get 0. I could kind of confirm that I'd get 0. Now, your calculator sometimes will confuse you. Now I'm finding second calc intersect, the intersections between this graph and the graph of y equals 0. Your calculator may confuse you here, and they give you like this weird number with an E. That's just, I don't know, sometimes it does, sometimes it doesn't. Here it's telling you, okay, 0. Now I'm not changing directions at 0, so I'm not going to include that since we're starting from 0 to 8. So I'm just going to find these two locations here. Now what's going to be great about this is like our one known position is at t equals 5. Okay, so I got 2.7123. That is the first time when my velocity changes. And maybe we'll just graph velocity here, do a sign analysis. My velocity is negative until 2.7123. Then it's positive until this value, which I'll find in a second, and then it's negative. So here's where I change directions, those two things. Now, what's going to be my position? Well, this is a time. It's not a position. It's a time. We are graphing x's instead of t's. This is very, very important. The x-axis is now a time axis, okay, not a position axis. The y's are my velocities. The x's are the times. So this is the time in which my velocity changes. This is when my particle changes from going from the left into the right. This time is before my known position. So I need to set up my equation like this. My known future position equals my unknown position from the past plus my displacement between the two. Now, here's a quick little trick that I taught you about, I believe, in the first semester, at the end of the semester, is that when you find an intersection, that number is stored as x. Okay? And we could decide to store that and press the store button down here as a different variable just to help you. Okay? Now watch this. I know x of 5 is 3. I don't know x of 2.7123. I can, instead of copying down the entire number, just store it, pull up my cos x plus 2. Instead of having to type this number in, I'm just going to use a to 5. Okay? And I see I've displaced 4.128 from this value to that value. So where did I start? Negative 1.218. Okay? And now let's go ahead and go back in here and find the other location. We can store it as B. It's my other zero velocity. Cool. This is stored as X. I'm going to now store it as B. This is in the future. So now I have the formula, my unknown position from the future compared to what I do know, equals my known position from the past. And I also could use this 2.7123 position now. That's another known position. And now this is important. I'm going to go from 5 to 5.853. What is the displacement between those two times? Grab this guy. Now I'm going from 5 to B. Add that to the position of 3. And that's my position at the other time. Okay? Okay. Now, we could and we will want to know where I started and where I ended. Okay, but for right now, let's not worry about it. Let's think about my dude's motion. I know his position at 2.7123 seconds was at negative 1.28. So here's negative 1.218. Here he is at the 2.713 second. I know he gets to a position of 3 after the 5th second. And then I know he gets to a position of 4.041 at the 5.853 second. How did he move? He started somewhere. He moved to the left. He probably started right like around here. We could find that, but I'm not going to bother. He moved to the left, got to this position. It's a minimum position. When I change directions, it's going to be a minimum or maximum. He then moved to the right. We got to the 5th second where he's there, right here. Then he kept moving to the right till this second, the 5.853 second. That's my position of 4.041. That'll be a max position. And then to finish things off, till the 8th second, he ends up moving to the left. How far? I don't know, but I could calculate it if I wanted to. And we will eventually want to, so that we can talk about overall max and min positions. And that's motion. All right, this is a good one because I have x of 0, so I know where I start. I could really figure out my overall motion here. Let's hide this guy. Let's break out the e to the negative guy. We're going from 0 to 4. Change position, change directions, to two locations again. Same deal where I start at 3. My velocity is gonna be negative until this first value. It's positive until this second value, which looks to be like 2, but it's not gonna be 2. And then it's negative. Okay, so I change directions at these two locations. I already know x of 0 is 3. I'll be able to figure out like how far I move to the left, how far I move to the right. Boom. So let's set up some equations after we find some intersections. Let's find this intersection. I'll store it as A. And the other intersection, I'll store it as B. Switch to the y equals 0. Might be easier and faster to get to the other intersection. 1.989. That'll be B. Okay. Make sure you go through that process of storing it. Store as B. All right. They're both in the future, so my position at 0.145 ... will equal my position at 0 plus my displacement between those two times. And you don't have to write this entire v. If you just wrote v of t, that's fine. Let's find that 40e to the. There it is. Okay, so from 0 to A. Negative. So I've started at a position of 3. I then have displaced. I've moved to the left 3.43 units. My position at this first time when I change directions, this will be a minimum position, is 2.656. Then my position at 1.989. We could use this position if we wanted to, and the displacement between here and here to figure out how much I move to the right, if you wanted to. Why don't we do it? So this position equals my known position at 0.145, which is this, and then plus my displacement between those two. And I'm just going to use v of t dt because that's v shown there. So let's go grab this guy. And instead of 0 to B, I'm going to go from A to B. A is the 0.145 and B is the 1.989. This is great because this shows me how much I've moved to the right over this interval. It might help me describe my motion a little bit better. $11.665. Okay, so motion. Dude on a number line. Dude started at a position of 3. Here's my position of 3. This is t equals 0. He moved to the left just a little bit. He moved to the left negative 0.343 units. He ended up at a position of 2.656, and he's there at the 0.145th second. Here he is there. Then he moves to the right a total of 9.009 units, and he ends up at this max position of 11.665 at the 1.989 second. It's like how much F is going up. We're finding maxes and mins just without really being asked to find the max and min. Max and mins will be next class. Okay. We're given velocity. We're given the displacements underneath it. We're giving the areas underneath it. So that's good. What is this telling you? What is this 5 telling you? It's how far I've moved to the right. What's this between 0 and 3 seconds? What's that? How far I've moved to the left. What's this? How far I've moved to the right. If you know where you started, you can really, like before answering or reading any question, know exactly what's going on. I start at a position of 2 at time 0. After 3 seconds, I'll move to the right 5. So that means I'm going to 7. That'll be at 3 seconds. Then I'm going to move to the left 3, which means I'll be at a position of 4 after 3 more seconds. And then I'll move right 1, ending up at a position of 5 after 7 seconds. What's the displacement from 0 to 6? Right 5, left 3, right 1. It's just the accumulation of my velocity from 0 to 6. Oh, sorry. 1, 2, 3, 4, 5, 6. Right 5, left 3. Right 5, left 3. 2. That's my displacement. Right 5, left 3. I've displaced 2 from 2 to 4. What's the position at time 3? Well, I started at a position of 2. My displacement from 0 to 3 is 5. So start at 2, add 5. Where did I get to? At 7. I have it right here. Final position. Right 5, left 3, right 1. I ended at 5. Or my position at time 7 equals, I don't know, it doesn't matter which position you have because you have everything you need. Maybe you say 0, 0 to 7, whatever you want to do. I started at a position of 2, right 5, I'm at 7, left 3, I'm at 4, right 1, I'm at 5. 5 minus 3 is 2, plus 1 is 3, 5. Did you have to do it this way? No. Could you have just done it right away, like the way that I did it, with like kind of understanding motion? Areas under velocities, the accumulations of velocities is total displacement, how much I've moved, then you'll be fine. Okay, but now I know, and this is a good one, a position at time 3. Okay, so this is important. I know when t equals 3 where I am. Now, it's important to be able to work backwards without maybe doing the formulas, just to kind of know what's going on. So I'm at a position of 2 at time 3. Here I am. Now, this means I moved to the right 6. I needed to move to the right 6 to get to this position of 2 at time 3. This is over 2 seconds. So at t equals 1, I need to be 6 to the left of this. That's going to be at -4. This accumulation tells me I moved to the left 2. Well, I needed to move to the left 2 to get to my position t equals 1. Well, that means I needed to start at -2. Move to the left 2, move to the right 6. -2 minus 2 is -4, plus 6 is 2. Boom, I've made it to position at time 3, which is 2. And then I finish off by moving to the left 3. Here at t equals 3, I'm at 2. Move to the left 3. I'll end up at a position at time at time 4 of -4. Okay. What's the displacement from 0 to 4? 1, 2, 3, 4. Left 2, right 6, left 3. Or -2 plus 6 minus 3, which is 1. Look at that. My overall displacement to the right 1. I started at -2, I ended at -1. It makes sense. What's the position of the particle at t equals 0? Well, I could say, if I wanted to, I could use this. If I wanted to, I could just understand. Or I could say my position at time 3, I know. That's in the future. 0's in the past. Between 0 and 3, I can find my displacement. I ended at 2. I don't know where I started, but my displacement is 4. So that means I must have started 4 to the left of 2. I must have started at -2. Yep. I started here. I had to move right 6 to get there. I had to move left 2 to get there. Compared to t equals 3, t equals 0 is left 4. That's my displacement between t equals 3 and t equals 0. This is t equals 0. This dude's head is freaking me out here. Okay. You don't even know about distance yet, but I bet you can figure this out. Now, distance is just like total amount moved. What is this is the question. I know I've moved a total of 13 units. So that means like I went right 6 and I went right 2. That's a total of 8. How many more do I need to get 13? 5, right? Well, if I put a -5 here, let's see. Right 6, left 5, that's a displacement of 1. And then right 2, that's a displacement of 3. Yeah, that works out. I don't know. Don't think that's a tough question, but we will talk more about distance in the future. All right, we already did part D in the last homework video, but I'll show you kind of 2 ways you could do it. Since this is a no calculator problem, and you're asked to find an unknown position, if it's a no calculator, you will be able to take the antiderivative. I would recommend you do that. So for part D, I would recommend you look at the 7.1 homework video for the way that I would recommend. I'm going to show you the alternate way, which is using the fundamental theorem of calculus, which says my position at time 4 will equal my position at time 0 plus my displacement between those 2 times, my accumulation of my velocity being my displacement. I have this as -2. I can take the antiderivative of this. Find the change in that from 0 to 4. So I'll have the -2 plus, I got 6 over pi sine, plug in 4, it becomes 2 pi over 3. It should have a plus c, but we know that the c's are going to go away, so I'm just going to remove it there. and then minus 6 over pi sine 0. Fortunately, the 6 over pi sine 0 is 0, so I just have negative 2 plus sine of 2 pi over 3, 2 pi over 3, 60-degree angle, root 3 over 2 is this. Do you have to simplify this? If you wanted to, but you'll find that this is the exact same answer as what we got from the homework 1 video. Again, we did do part D. I don't know if we did part D. We might have skipped it. But here we have velocity of Q. When does the particle change directions? We'll set the velocity equal to 0. I believe we did this, but then I'll just show you the alternate way to get the position besides taking the antiderivative and finding C. I get t minus 5, t minus 3. So I'm looking at t equals 3. I want to find my position at time 3. The alternate way, instead of taking the antiderivative and finding C, which you can do and which is what I would recommend you do if you don't have a calculator, you could say my position at time 3 for Q will equal my position at time 0 for Q, which is 5, plus my displacement. This is the alternate way. Probably would do the other way, take the antiderivative, find C using 0, 5, and then just plug in 3. Take the antiderivative. I'm including the plus C this time. I'm not forgetting about it. Know that the C won't matter. 27 divided by 3 is 9. 9 times 4 is 36. 15 times 3 is 45. Don't worry about the plus C. It's going to go away. You'll subtract 0. Leave your answer like this. It's a free response question. If you wanted to have some fun with it, this is going to be 9 plus 9, which is 18. 18 plus 5, which is 23. Okay? Now let's check quickly. Let's say we do have our calculator and there's a homework question. We just want to make sure our answer is correct. It's good to do that. Well, take my known position at time 0, which is 5, add. My calculator can find the displacement. It's not taking the antiderivative. Instead, it's just doing a bunch of arithmetic, accumulating from 0 to 3, which is the first time it changes directions. T squared minus 8t plus 15. 23. There you go. All right, here we go. Find the position at time 0. I have a calculator. I can't take that antiderivative. I can't find C. I can't then just plug in 0 into x of t because I don't know what x of t is. But I do know at t equals 4, it's very important to put this. I know x is 2. A lot of people like to put the 2 here. But t's go first. X's are positions on a number line. Well, I know this position in the future time. I'm trying to find the position in the past time. This is when I set up the x of 4 equals x of 0 plus my displacement between the two. How much did I have to move to get to this position of time 4 from my original? Kind of do the opposite to work your way backwards. Let's see what we got. X of 4 is 2. X of 0 is what I'm trying to find. 0 to 4, math 9. 1 plus 2 sine t squared over 2. .815. I had to move to the right overall. I might have moved right and left a bunch, but between the 0 second and the 4th second, I've ended up displacing 5.815. Where did I start at the 0 second? Well, 5.815 to the left of 2, or subtract that number, 2 minus that. Just solving the equation. 3 decimal places is all you need. Do part B. Write an expression involving an integral that's position s of t. Now we're used to s of t being x of t. Sometimes they like to use x of t, sometimes s of t. Just don't let it freak you out. Use this expression to find the position at t equals 5. I know s of 0 or x of 0 is 10. If you want to change from s to x, just make sure you say s of t equals x of t and you're fine. But let's just use s of t. My position at time t will equal my initial position. You could put s of 0 or you could put 10 plus my displacement from the 0 second to whatever time I want. Now, you're not comfortable with this yet, putting a t in a variable, but like it makes sense. Like if I wanted to find the position at 5, I'd put 5 here. So if I want to find the position at t, I'd put t here. And I'm just going to put v of t. It's already given to us. It's tough to write it down. Okay. So I want to find the position at 5. I know the position at time 0. I know the displacement because I have a calculator. Can't take the antiderivative of that. You might think you can, but you can't because this t squared, you can't undo the outside and stuff like that. So I got 10, which I'll add later. I got 0 to 5 of v, negative 2 plus t squared plus 3t to the 6/5 minus t cubed dt. That's my displacement. Do you see how long it took your calculator to get that? Why? Your calculator has to do a bunch of arithmetic. For a calculator, that was slow. And boom, we have our position at time 5. So I started at position 10. Between 0 and 5, I might have moved left and right a bunch, but my position at time 5 is 19 units to the left of my position at time 0. That's the displacement. That's it. Okay. Change this up from past years to try to make it easier to understand. I hope it is. I think the next lesson really fits in with what we were just doing, especially with changing directions. We're going to find max and min positions. And then the lesson after that is new stuff. But it's really lesson 2, lesson 3 is the heart of this unit. And hopefully we're good to go with that stuff later.